Hello. In this video we're going to take another look at the harmonic oscillator, which we looked at in the previous video, but this time we're going to look at it using operator methods, which is a lot more exciting. Okay, so here is the time-independent Schrödinger equation. So let's write the kinetic energy term as p squared over 2m, with p the momentum operator, plus half m omega squared x squared, where x is the position operator, and it's acting on eigenstates phi n and giving eigenenergies En. And again, the phi isn't really serving a purpose here. Let's just label this ket as n. And bear in mind that the wave function that we solved for in the previous video, which we called phi nx, here that's just given by the x projection of these states we're about to solve. But let's keep working with the ket formalism. Okay, so a very convenient trick that we can use in this problem, and actually many problems, is to define the following operators. So we define an operator A dagger to be this. It's a linear combination of the x operator and the p operator, and its Hermitian conjugate given by this. Remember that p and x are both Hermitian themselves, so they return to themselves under Hermitian conjugation. So these two operators have various names. They're called ladder operators, raising and lowering operators, where this is the raising and this is the lowering, and creation and annihilation operators, where the last term will hopefully make more sense by the end of this set of videos. So we can see straight away that these do not correspond to physical observables because these operators are not Hermitian. A and A dagger are different operators. But they are nevertheless useful. So let's put them to that use now as follows. So first consider what we get when we have A dagger A. It must be given by this. We can multiply this out. So we're going to get four terms. We'll get this term, this term, this term, and this term, just like multiplying out any quadratic. And this gives us the following, where we've been careful to keep track of the non-commuting operators x and p, and in fact this expression here is simply the commutator of those two terms. But we know that by definition our canonical commutation relation is that the commutator of x and p is I h bar multiplying the identity operator, and so multiplying through we find the result. Multiplying both sides by h bar omega, we find this. So this bit is just our time-independent Schrödinger equation. This is our Hamiltonian. We've got this extra term added here. So rearranging a bit, we find the following result for our Hamiltonian. And for our time-independent Schrödinger equation, well, we can actually drop the identity operator now because this acting on the state is just the number one. So a small technicality. And so this is then our time-independent Schrödinger equation. So let's consider this commutator. It's given by this, just inserting the forms of A and A dagger. Of course, x is going to commute with x, p with p, so we only get the x with p commutator terms, and so it reduces to the following, where this cancels with this cancels with this, and p commutator x is minus I h bar times the identity operator, and so the end result is this. The commutator of A with A dagger is the identity operator. All right, that's good. And the really important result is when we now check the commutator with the Hamiltonian. So the commutator of the Hamiltonian with A dagger is given by this, because remember the Hamiltonian is just h bar omega multiplying A dagger A plus a half times the identity operator. By definition, this commutes with everything, so this disappears. So we're left with this commutator to evaluate. But this is quite straightforward because we can just multiply, we can just expand it. That's just writing the commutator out. And we notice that we have an A dagger on the left of everything, so we can write it as follows. But this is just the commutator of A with A dagger, which we know is just the identity operator. And so this is our result. Similarly for H with A, we find just minus h bar omega times A. Okay, so that's all well and good, but now we can use it to actually derive the full set of solutions for the energy eigenstates and the energy eigenvalues. So let's do that now. Actually, let's do it in the next video. What are you up to?